Hi again. Today I want to take a look at calculations with regards to measurements and scientific data. To do this, I'm going to take a look at an example problem. We're going to try to determine both the volume and the density of this rubber stopper. To determine the volume of the rubber stopper, we place it in a partially filled graduated cylinder and observe the change in volume. And to determine the mass, we'll put it on an electronic balance. Now, when we do calculations, our first decision has to do with the uncertainties that are present. If we have no uncertainties present, there's one technique we use to solve the problem. However, if we do know the uncertainties, then there's a second method that we'll need to use. So when you see this program, I'm going to divide it into two parts. In the first part, I'm going to look at when the uncertainties are not known, and in the second part, I'll look at when they are known. So here we have the data when the uncertainties are unknown. The first thing I'm going to try to determine here is the volume of my rubber stopper. To do that, I'm simply going to subtract the volume before and the volume after, and I come up with 7 milliliters on my calculator. Now, just to note here that a milliliter is exactly the same size as a cubic centimeter, so I could use the two interchangeably. Now, the rule governing what I should write down for my answer is that my final answer should be quoted to the same number of decimal places as my least precise data. An examination of my two volumes indicate that they both have one decimal place. As a result, my final answer should also have one decimal place. So right now, it doesn't have a decimal place, so I would simply insert one and make it 7.0 milliliters. Had you had a number there, you would round it off then to one decimal place. Now let's look at how we would calculate out our density. Density, recall, is mass over volume. Now in this case, to avoid any rounding off errors, I'm going to use the subtraction of my two volumes to come up with the change in volume. And I put these numbers in my calculator and I obtain the following answer. Now I'm not quite sure how to round that off yet, so I'm going to take a look now at the rule. The rule states that my answer should be quoted to the same number of significant digits as my least significant number, not decimal places. It has to do with significant digits. Now, my first volume has 3 significant digits in it, my second volume 3, and my mass 4. So at first examination, I might say that my final answer should therefore have 3 significant digits because that's my least significant number. But recall that in orders of operation, when we can do the subtraction of those two volumes, we arrived at 7.0 milliliters, which really only has 2 significant digits in it, the 7 and the 0. As a result, that number on the bottom only has 2 significant digits, and my final answer should only have 2 significant digits. As a result, I would round that final answer off to 2.4 grams per milliliter, or grams per centimeter cubed. So those are our two rules governing, first of all, subtraction and addition. We look at decimal places. However, when we're multiplying and dividing, we look at significant digits. Now, if the uncertainty is known, we handle the problem differently. First off, to find the volume of my stopper again, I subtract the two. Now here I'm writing down 7.0 with a bunch of zeros in brackets to indicate that I don't want to have any rounding off error, because perhaps you had more complicated volumes than what I had. But the idea here is you don't want to do any rounding off till the very end of your calculation. The absolute uncertainties in this case should be added together. So in this case, the 0.5 and the 0.5 are added together to indicate the uncertainty in my final answer is plus or minus 1 milliliter. Now, reduce the significant digits in our absolute uncertainty to 1 digit. This is common practice. So when I add those together, it shouldn't become 1.0 because that has 2 significant digits. I'm just going to reduce it to 1 milliliter, which has 1 significant digit. I now bring over my numerical answer from the calculation. I have to bring these two into agreement, meaning that they both must have the same number of decimal places. So my 1 milliliter is good to the ones column. I have to round the 7 off to the ones column. So my final answer here would be 7 plus or minus 1 milliliter. Now let's take a look at the calculation of the density. Again, to avoid any rounding off errors, I use the original data, and I'm going to record, or at least keep in the memory of my calculator, all of the digits. The rule governing how I deal with uncertainties here is I add together the relative or percentage uncertainties. So to find the relative uncertainty in my density, I have to add the relative error of my mass and the relative error of my volume. Now the relative error of my mass is 0.01 over 16.43, and the relative error in my volumes, recall, from when I subtract them, was 1 over 7. And again, if you had data that didn't come to exactly zeros, you want to keep that original data with all of its decimal places. Anyway, upon adding those two together, I'd like to point something out. The error that's in my mass is 0.06%. The error in my volume is around 14%. This is important to note because if one is trying to improve an experiment, at least the precision of an experiment, one of the things you may want to look at is what is your biggest source of error from? And in this case, it's the volume. So to improve this experiment, I would really want to look at a different technique or an improved technique of measuring my volume. Anyway, at this point I know I have about 14.3% error in my answer. I'm going to convert that to an absolute error by multiplying 14% times my answer, indicating 0.349 and so forth grams per centimeter cubed. That is now my absolute error. As before, I want to reduce that to one significant digit, so it becomes 0.3 grams per milliliter. And now I want to bring it into agreement with my numerical answer. My error has one decimal place, so as a result, so must my density have one decimal place. So I'm going to round that off to 2.4. So there's again a look at the two different techniques that you use to calculate your error. If you have any questions, please don't hesitate to ask.